Welcome to Center of Math's Advanced Knowledge Problem of the Week. For this week's problem, we want to show that the polynomials over the field Z3 in terms of x, the quotient of that with the ideal generated by x squared minus 1 is isomorphic to Z3 cross Z3. So to do this, we can explicitly establish the isomorphism. So for some polynomial f in Z3x, we're going to have some homomorphism sending this polynomial to a member of Z3 cross Z3 by the rule theta of f gives us f of minus 1 comma f of 1. And so first thing, clearly this is well defined. Plugging in f of minus 1, f of 1, it gives us one value. So we can establish this as a ring homomorphism by the usual checking all the rules apply. So just by using some of the simple properties of multiplying and adding polynomials, if we take theta of fg, that's fg of minus 1, comma fg of 1. And then our ring z3 cross z3, we multiply component-wise. So this is equal to just f minus 1, f of 1 times g of minus 1, g of 1, which is equal to theta of f times theta of g. So that checks out. Theta of f plus g is just, again, f plus g of minus 1, f plus g of 1. So in our ring, we can just pull out the addition. So this is f of minus 1, comma f of 1 plus g of minus 1, comma g of 1, which is then again theta of f plus theta of g. And so, yeah, and so this is a ring homomorphism from Z3x to Z3 cross Z3. So now if we find the kernel of this, also note this is surjective. We just take Z3x to be 0, 1, 2. This is surjective. We can get any value from Z3 cross Z3 from our homomorphism. And so from the first isomorphism, the fundamental homomorphisms theorem, we just want to find the kernel, and then the image is isomorphic to the ring quotient, the kernel. And so the kernel clearly we have any polynomial multiple of x squared minus 1. We plug in 1 or plus or minus 1 to that, it's going to give us 0. And so by the definition of the kernel, theta of f in the kernel will give us just 0, 0, the 0 element of our ring, Z3 cross Z3. And so, yeah, so clearly x squared minus 1, the ideal generated by x squared minus 1 is clearly in the kernel. We want to prove it's all the kernel. If f of minus, since for theta of f to give us 0, 0, we want f of minus 1 to give us 0, f of 1 to give us 0. And so this implies x plus 1 will divide f of x. You can use any number of division theorems to prove this. And x minus 1 divides f of x. And so therefore, x squared minus 1 must divide f of x in the kernel. And so this proves the kernel is in fact contained within the ideal generated by x squared minus 1. And so it must be the whole ideal generated by x squared minus 1. And so kernel theta equals x squared minus 1. By our isomorphism theorem, we have Z3x quotient, the ideal generated by x squared minus 1 is isomorphic to Z3 cross Z3. Thanks for watching. Please check out our blog on centermath.org and check out our Facebook and Twitter. Thank you.